Hello students, welcome to our second lecture of module B, and in this lecture we are going to discuss Euler's equation of motion. We will derive it and then we will look into its three special cases. While first special case would correspond to steady and non-uniform flow, and this will also give us Bernoulli's equation that you must have encountered in fluid mechanics, and then we will discuss two other cases, that is what is the steady and uniform case, and finally the most generic case, which is unsteady and non-uniform flow. So for some of you it may be recap from fluid mechanics, but now we will use the terminology consistently throughout our lectures on open channel flow. So in any case, please watch the terminologies and derivations very carefully. So let us consider that there is a channel in which there is some water that is present, and here we consider an any direction, generic direction del S. So if our direction here is del S and perpendicular to this del S, let us consider another direction del N, and perpendicular to this paper, the the width of this section is considered as 1 unit. So cross sectional area would become del N into 1. And we will try to write this Euler's equation of motion for any generic direction del S. Let us say that because of this fluid, pressure that is acting on this surface is equal to P, and assuming that pressure is varying at the rate of del P upon del S, del P upon del S, and if width of this section is del S, that so see this is partial del S and this is delta S, just for, so this represents infinitesimally small change, and the delta S is the length of our element. So we can safely write this pressure as P plus del P del S into delta S. And if this angle of inclination is theta, then the weight component that would be acting in downward direction is going to be W sine theta, and W is going to be volume of this particular element, which in this case is equal to delta S times delta N times rho into G. And if we consider our Z direction to be positive upwards, we can clearly see that our sine theta is going to be rate change of Z with respect to S, and here we can say that this is in the direction of S, and if the drop in Z is equal to from Z1 to Z2, it is definitely going to be negative, and that's where sine theta is already taken care to account with a negative sign. Now if we look at the force that is acting on top surface, it is given by P into del N into 1, and for sake of simplicity we will not keep on writing this 1 again and again, and this would be multiplied by this area on which this is acting, which is equal to, so this is our total force that is acting, pressure multiplied by area. And since this is acting along the direction of del S, we will consider it as positive. Anything that is acting opposite to this direction of delta S would be considered negative, because we are deriving expression around this generic direction. So we can write this second term as P plus del P upon del S into delta S multiplied by delta N, and our force virtue of weight is acting again in downward direction. So what we will say here is that this is equal to plus rho G del S del N into sine theta, and we can say that this is the net force that, or the resultant force that is acting on this element under consideration if we consider non-viscous fluid. Now because we have not accounted for any term related to the shear stress acting by virtue of viscosity, and that's where we are saying that this expression is applicable only to non-viscous fluid. Further, we can say that we know that our force is equal to mass into acceleration in the direction under consideration. So we can write this as MAS, and upon expanding, we can say that this is P delta N minus P delta N minus del P upon del S into delta S into del N, and sine theta is equal to minus dz upon ds. So we will write this as rho g del s into del n. Sine theta is given by del z upon del s. As we discussed here, sine theta is del z, and this negative sign would take care of that. Now, mass of this particular element can again be written as dn, or just to avoid confusion, del n into del s multiplied by rho multiplied by as. This becomes our mass, and these two terms cancel out. So we can simply write this as minus del of del s p into del s del n plus g rho del s del n into z, because we have taken out this delta terms. So upon simplification, del n and del s is common across all the terms. We end up with an expression that rho as is equal to minus del upon del s p plus g rho, and this g rho can be written as gamma multiplied by z. So rho as equal to minus del s p plus gamma z. And if we talk about acceleration, let us say our acceleration is function of space and time, or we can say that acceleration is rate change of velocity with respect to time, and our velocity is also function of space and time. We can say that our acceleration can be written as del vs upon del t plus partial derivative of velocity with respect to space, because we have already accounted for differentiation with respect to time. So second term would be del vs upon del s multiplied by del s upon del t. I'm sure you can relate that this is the total derivative, and we have split into partial derivatives using a chain rule here. So substituting these values, we can clearly write that rho times del vs upon del t plus vs into del v upon del s, it becomes equal to minus del upon del s p plus gamma z. And this equation, which looks so cumbersome but would make lot of sense as we move forward, is known as Euler's equation of motion, and it is applicable to both unsteady as well as non-uniform flow in non-viscous fluid, because this was our first assumption when we started the derivation. However, there is a term with respect to time, there is a term with respect to space, and we have not accounted for any frictional forces. Now if you look at this term, this is rate change of velocity with respect to time, and we also call this as local acceleration. This is rate of change of velocity with respect to space, and this term is called as convective acceleration. And now we will look into the specifics of this particular equation, that how we can derive the special cases using this equation 1. So the first special case that we will consider here is that of steady flow. So as you know, in a steady flow, rate change of any quantity x with respect to time becomes equal to 0. That would mean our local acceleration term can be safely written as 0, and we can write this expression as rho times vs del v upon del s equal to minus del upon del s p plus gamma z. And if we bring all the terms here, we can write it as rho vs del v upon del s plus rate change of p plus gamma z with respect to s equal to 0. And if we take integral on both sides, we can write this as, or multiplying both sides by del s, our term would become vs rho del v plus del p plus del into gamma z, and this is equal to 0. And if we take integral, and we are not adding any limits here, so we can write this as half into, this is velocity del v, so this would become v square by 2, and one term of rho is already present. Integration of pressure would simply become p, and this term would become gamma z, and this would be equal to constant, because as I said, we are doing a indefinite integral or integral without limits. So if we divide this term by g multiply by rho, we can simply say that this is g times rho, and this is also g times rho, and g and rho are going to be constant if we consider our fluid to be incompressible, because that's how we were able to take this limits and this integral, because we considered our flow is non-viscous as well as incompressible, which is not a bad assumption to make in case of open channel flows. So this is equal to gamma, so our equation reduces to half into v square upon 2g plus p upon gamma plus z equal to constant, and which is famously known as Bernoulli's equation, and it is applicable to steady and non-uniform flow, because we have taken integration with respect to delta s, and of course it is applicable along a streamline for all the assumptions that we have stated before. But here the special case is we have eliminated the term where local acceleration was accounted for, and hence we would widely use this particular expression into open channel flow wherever we have a steady flow condition being met. Now after this, the second case that arises that we have to consider is that when flow is steady and uniform. If we go back to the original Bernoulli's equation, we clearly see that there are terms of time as well as space. When we talk about steady flow, we know that del Vs with respect to time would be equal to 0. And when we talk about the uniform flow, any differentiation or rate change with respect to space should also be 0, which implies that del upon del S of P plus gamma Z becomes equal to 0. And we can again say that del P plus del of gamma Z equal to 0. And when we take integral, we can say that P plus gamma Z becomes constant, and if we divide both sides by gamma, this becomes a new constant C prime, and again we get the condition which is famously known as the hydrostatic condition. That means if our velocity is not changing, then if we just look at the summation of these hydrostatic pressures because of virtue of elevation of point above the datum and because of hydrostatic pressure, that is going to remain constant if our velocity is not varying. And this makes sense, because if velocity is not changing, then between any 2 points we can write half of v1 square upon 2g plus or v1 square upon 2g plus p1 upon gamma plus z1 equal to v2 square upon 2g plus p2 upon gamma plus z2. And if v1 is equal to v2, because that is what we mean about the uniform flow, our velocity term will cancel out and we would be left just with p1 upon gamma plus z1 equal to p2 upon gamma plus z2. And finally, when we talk about our case 3, where flow is non-uniform as well as unsteady, in that case we can write our expression of Euler's equation of motion as rho into del Vs upon del T into ds plus Vs into del V upon del S into ds plus P plus gamma Z equal to C. We have done nothing special, but we have multiplied all the both the sides with the term of delta S, so that we can eliminate these quantities here, so that we end up with an expression which looks like rho into del Vs upon del T into ds plus V square by 2g plus P upon gamma plus Z equal to C. Now you're already familiar with these three terms. These three terms are coming from our Bernoulli's equation. So in Bernoulli's equation, we had an assumption of steady non-uniform flow. Now, but because of non-steadiness, we cannot reduce this term to zero, and hence we end up with this peculiar terminology which involves the integral of derivative of rate change of velocity with respect to time. And when we talk about cases of open channel flow, this term is usually not easy to calculate, and hence the non-uniform unsteady cases have to be dealt separately. And when we go to gradually varying flow, where we talk about understanding of one dimensional Saint-Venant's equation, we will again revisit that, and we will clearly try to understand how difficult it is to solve this equation analytically. So for next few chapters, our discussion would be primarily around case 1, and we will extensively use Bernoulli's theorem, and case 2, where we will use steady and uniform assumptions wherever applicable. And using these concepts, we will try to understand the open channel flow in greater detail. Now, before we go ahead, I will leave you with a small exercise. That is, for example, let us consider that this is our datum and our channel bed is at some height d1 from this datum, and a there is a water level which is located somewhere here, and at any point here we have some pressure P1. Height of this point above the channel bed is equal to B1. The question is, can you write the expression of Bernoulli's equation at this point? And you can assume that velocity is uniform throughout this channel, and it is given by V. And your final expression should be in terms of P1. You can use gamma, you can use B1, you can use D1, and you have to use velocity and of course acceleration due to gravity. Now once you can develop this relationship using these terminologies, we will define a very special term called as specific energy, which would be widely used throughout open channel flow, but it would find its roots into our Euler's equation of motion. And we will start our discussions around specific energy into our next lecture. Thank you.